Hello students, how are you? I hope you are doing good and you are well and safe at your home. I welcome all of you on this educational platform. In the continuation of the periodic table, in the continuation of the periodic properties, today we will discuss about two more periodic properties, that is electron negativity and electron gain enthalpy. So we shall discuss what is electron gain enthalpy, what about the electron negativity, and also what about the inert pair effect. What is the consequences of the inert pair effect, that we shall discuss in this unit, and this is all about the periodic table. So let's come and study about this. In the previous session, we discussed about the radius of atom and ionization enthalpy. Now in this segment of this chapter, classification of elements and periodicity, we shall discuss about electron negativity and electron gain enthalpy. So what do you mean by electron negativity, or what do you mean by the term electron gain enthalpy? See, when an electron is added to a neutral gaseous atom, means you have to add an electron in the neutral gaseous atom, and then there is a formation of negative ion, that too in gaseous state, of course. See, whenever you add any electron to the neutral atom, some sort of energy is released. So the enthalpy change during this process is called as electron gain enthalpy. Do you know why we are calling this as the enthalpy change rather than released energy? Because when you add an electron to a neutral gaseous atom, it is not like that energy is always released. Sometimes if the species is extraordinarily stable, then energy is absorbed also. So when you add electron to the gaseous neutral atom, some energy is involved. It is better to say that some energy is involved, might be released or might be absorbed, and that energy is called as electron gain enthalpy or electron affinity. See, electron affinity is the old term. Nowadays we usually refer this energy to the electron gain enthalpy. Now another question which come in your mind, that whether this energy is always released or absorbed. So as I told you, this energy could be released energy or could be absorbed energy, but for most of the time, for most of the atoms, this energy is released energy. So this is, most of the time it is negative energy. So since delta Heg is negative, this is exothermic process. You know guys, what is the meaning of this Eg? This Eg stands for electron gain, and delta H is, you know, enthalpy. You better know that delta H is enthalpy and Eg is electron gain, right? So when an electron is added to a uninegative ion, what happens? See, suppose you tried to add one electron in the neutral gaseous atom and you somehow added the electron. When you added one electron to the neutral gaseous atom, there is a formation of uninegative ion, right? Now you further want to add one more electron to this uninegative ion. So what I'm trying to say is, what will happen when you try to add one more electron in this uninegative ion? The pre-existed negative charge, the negative charge which is already there, will repel the coming new electron. We know, students, that like charges repel each other. So this coming new electron will be repelled by the negative charge, and thus it will form x minus 2. So it is very difficult to form x minus 2 because the coming electron will be repelled by this pre-existed negative charge. So it is quite difficult to add an electron in the uninegative ion. That is the reason why delta Heg for the second instance is always positive. So in this case, energy is absorbed, and this is called as, students, second electron affinity or second electron gain enthalpy. So here delta H is positive, and of course it should be positive because here we are adding electron, and when you are adding electron, then the process will be endothermic. So energy is absorbed because you are adding electron in the anion, right? Now what is the unit of electron affinity? Since electron affinity is the energy, its unit is electron volt per atom, kilocalorie per mole, or kilojoule per mole, or kilojoule per atom. You can also measure this in kilojoule per atom. Whatever the energy is in kilojoule per atom, if you multiply this energy by the Avogadro's number, it will become kilojoule per mole. Now, trend in the electron gain enthalpy or electron affinity. Students, you already know what is the meaning of trend. Trend means variation. So when you go left to right in the period or top to bottom in a group, what is the trend? So what is the trend in the period? Electron gain enthalpy increases as we move from left to right across a period. So when you go left to right across a period in the periodic table, electron gain enthalpy increases. And what comes in the end of periodic table before the inert gases? Halogen. Now this explains why halogen has the highest electron affinity in the periodic table. They have the highest electron affinity in the periodic table in their respective period. And what is the reason behind this? Why this electron gain enthalpy increases across the period? Because atomic size decreases. When the atomic size decreases and the effective nuclear charge increases, tendency of nucleus to attract the coming new electron increases, and it becomes more easy to add an electron in the isolated gaseous atom. That is the reason why it becomes more negative. So electron gain enthalpy in the group. Electron gain enthalpy in the group decreases as we move from top to bottom. So when you go top to bottom in the periodic table in a group, I say electron gain enthalpy decreases. Now reason is quite obvious. It is just reverse of the previous one. When you go top to the bottom, atomic size increases and effective nuclear charge eventually decreases, and this leads to decrease in electron gain enthalpy, right? But we have few exceptions. We also have few exceptions. Number one exception is inert gas. Students, you already know that inert gas have configuration completely filled. They have completely filled electronic configuration, which means their outer shell is completely filled and it is stable. When the electronic configuration is ns2np6, where outer shell is completely filled, it is a stable configuration. And if the configuration is stable, it is very difficult to add an electron because it will destabilize the species. Species is already stable, and if you will try to add few more electrons, it will destabilize the species. So definitely it repel the coming new electron, and that is the reason why when you try to add electron in the inert gases, their electron gain and enthalpy is highly positive. Large amount of energy is absorbed if you will try to add electron in the inert gases because they are not ready to gain electron. And the another exception, which is comes in the halogen family, also in the oxygen family. Like I told you in the previous slide, when we go down the group, what happens when we go down the group? I said electron gain enthalpy decreases. So the normal anticipation, what we will expect, that member of third period will have lesser electron gain enthalpy than the second period member. This is the expected value. Electron gain enthalpy of fluorine should be more and chlorine should be less. But just reverse of that. The reality is just reverse. Actually, electron gain enthalpy of chlorine is greater than fluorine. Or you can say that electron gain enthalpy of the third period element is greater than the second period element, because the same kind of exception found in the Oxygen family also, there also this exception is there. Member of third period will have more electron gain enthalpy than the respective member of the second period. It was expected that chlorine will have lesser value of electron gain enthalpy than fluorine, but in reality it has more electron gain enthalpy. And the reason, here is the reason. The reason is very small size of atom of the second period. In the second period, d subshell is absent, size is very much small, and that is the reason why their electron gain enthalpy is less. And because of this small size, electron density is high, and when density is high, inter-electronic repulsion which comes between electron and electron, it becomes more. For the species like fluorine, because of the very small size, electron density becomes very high, and because of the strong electron-electron repulsion between them, their electron gain enthalpy decreases in comparison to the member of respective third period. Alright, so this was all about the electron gain enthalpy. Now, next in this chapter, we shall discuss about the electron negativity. Students, what is electron negativity? Electron negativity is the tendency. You know what is covalent bond? If I ask you what is covalent bond, you all must be knowing that covalent bond is simply sharing of electron. In a very simple example, if I take example of two atoms, hypothetical A and B, there are two electrons which are shared by A and B. One electron belongs to A, one belongs to B, and now it is shared. So now this shared pair, it belongs to both of the atoms, A and B. Technically, it is shared by A and B, and it belongs to A and B both. So it should remain exactly in the middle of, both atom A and B. But actually, in reality, this does not happen. A try to pull this electron pair toward itself, and the same attempt is done by B. Both the atoms A and B, they try to attract this shared pair of electron towards themselves, and this tendency to attract shared pair of electron in the covalent bond is called as electron negativity. So you see, it is qualitative measurement of the ability of an atom in a chemical compound in covalent bond to attract shared pair of electron toward itself is electron negativity. So if some atom is in the free form, it is not forming any covalent bond, the atom is completely free, absolutely free, you would not be able to define the electron negativity. We never define electron negativity for free atoms. What does it mean? I mean to say, you cannot define electron negativity until and unless there is a formation of covalent bond, because the primary definition of electron negativity is tendency to attract shared pair of electron. If electron pairs are there but they are not shared, you would not be able to define the electron negativity. So there is no electron negativity for a free atom. It can only be defined in presence of chemical bond, moreover covalent bond. Since electron negativity is a tendency, it is an ability, you cannot measure it. Tendencies cannot be measured. They may be high, they may be low, but they cannot be measured in terms of the numerical values. So unlike ionization enthalpy, yes, you can measure the ionization enthalpy. Yes, you can measure the electron gain enthalpy, but you cannot measure the electron negativity. Let me give you an example. Suppose I want to measure some property of yours. I can measure your height. If I want to measure your height, yes, I can do this. If I want to measure your mass, yes, I can do this. I can measure your mass, I can measure your height, but can I measure your tendency or your ability to study? How many times you study in a day? That is your ability of studying. Every student has different ability of study. Can we measure that? Can I ask you a question that how much able you are for studies? No, you cannot measure it. Yes, for some students this ability is high, for some students this ability is moderate or low, but you cannot measure it mathematically. You cannot have the mathematical value. That is the reason why we cannot measure electron negativity as such. It is not measurable quantity. And also electron negativity has no unit. This was the question in competitive entrance examination few times. Which of the following is unitless? Ionization enthalpy has a unit, electron gain enthalpy has a unit, but electron negativity has no unit. It is unitless, right? So how do we measure electron negativity? If we cannot measure electron negativity, it is not measurable. How would we be able to measure electron negativity? We measure electron negativity on different scales, out of which 3 scales are common: Pauling scale, Mulliken scale, and Arnold-Roscoe scale, out of which this Pauling scale is the most common scale. It is most used scale. Most of the time when I say electron negativity of this atom is this, electron negativity of this atom is that, in the normal terms we say that is in Pauling scale. So we measure the electron negativity over various scales, right? Like Pauling scale, Mulliken scale, Roscoe scale. So first we shall study about the Pauling scale. It was given by a brilliant scientist, Linus Pauling. Linus Pauling, an American scientist, he assigned arbitrarily a value of En 2.1 to hydrogen. He gave the value of electron negativity to hydrogen 2.1. He said that electron negativity of 2.1 is of electron negativity of hydrogen is 2.1, and this value was given arbitrarily. And what about the other elements? What about the other atoms? The electron negativity of other elements calculated with respect of the hydrogen. The value which is given to the hydrogen was 2.1, and for the other element this value was calculated based on this value, right? This was the Pauling scale. Another scale is the Mulliken scale. Mulliken scale is nothing, it is just the average of ionization energy, IP. Do you remember what is IP? Let me remind you. IP is the minimum required energy to remove electron from an isolated gaseous atom. And electron affinity, which we studied in the same lecture, in this today's lecture, couple of minutes back. So if you take the average of IP and electron affinity, average means sum and divide by 2, that is called as electron negativity. And this value of electron negativity is on Mulliken scale. But there is one limitation of Mulliken scale, and what is that? The value which we calculate on Mulliken scale is applicable only for monovalent elements like sodium, like hydrogen, like lithium. It is not applicable for the multivalent atom. Now what are the trends in the electron negativity? What trends you will see in the electron negativity? You know, students, what is the meaning of trend? Now as we are approaching end of this chapter, I hope now you're getting what is the meaning of trend. Trend means variation, and we see variation by 2 ways. Number 1, in the period we see the variation left to right, and in the group we see the variation top to bottom. So now we shall see the trend in electron negativity. Here is the trend in the group. Students, in the group, electron negativity decreases as we move from top to bottom. And why is that? What is the reason? Here is the reason. Now you are capable to answer this question. What happens when we go down the group? When we go down the group, atomic size increases, and as the atomic size increases, simultaneously shielding effect increases because of the increased number in electrons, and because of that size increases. If the size increases, tendency to gain electron, tendency to attract shared pair of electron decreases, and that is the reason why when we go down the group, electron negativity decreases continuously. You can see the value. for group first A, alkali metal and halogens. Have a look at these values. Now in these values, you see electron negativity for lithium is 1, for sodium, potassium, rubidium and cesium, it decreases continuously. Electron negativity for fluorine is 4.0, which is also maximum in periodic table. It is maximum in periodic table. So the value of electron negativity is maximum for fluorine, which is 4.0, and these values are on which scale? Like I told you, the most common scale is the, yes, you are right, Pauling scale. So electron negativity of fluorine is 4 over the Pauling scale. It might be different over the Mulliken scale, but the common scale is Pauling, and we used to calculate the value for Pauling scales, right? Now the another trend in electron negativity is in the period. Now before going through this, first we should think what happens when we go left to right in a period. What happens first when we go left to right in a period? Size decreases. And what about the effective effective nuclear charge? Of course it increases. So when we move across a period from left to right, then atomic size decreases. Eventually effective nuclear charge increases and tendency to attract electron increases. Tendency to gain electron increases, and as a result electron negativity also increases. So when you go left to right, electron negativity increases. That is the reason why in the end of period, just before inert gases, for the halogens, electron negativity is maximum. Just before the inert gases, electron negativity is maximum. This is the reason why. Here are some value. Here are some figures, data in order to support the fact. For the period second, lithium, beryllium, boron, carbon, nitrogen, oxygen and fluorine. This is the value of electron negativity which you see increases continuously. And for the third period, sodium, magnesium, aluminium, silicon, phosphorus, sulfur and chlorine, you see there is a constant increase in the electron negativity. So in the given period, halogen has the highest electron negativity, and like I told you, the most electron negative element in the entire periodic table is fluorine, which is 4.0 for Pauling scale. So electron negativity of fluorine is 4.0 for Pauling scale. Now what factors affect the electron negativity? Electron negativity depends on which factor? Number one factor is nature of bonded atom. Means those atoms which are forming covalent bond, what kind of nature they carry, whether they have same electron negativity or they are same kind of nature, means both are electropositive or both electronegative. One is electropositive, another is electronegative, or vice versa. The second factor which affects the electron negativity is atomic size. See, smaller the size of atom, smaller will be the distance between electron and nucleus. In this case, nucleus will easily gain the electron. It will easily attract electron, and here electron negativity will be high. On the other hand, for the larger atoms, there is a large distance between electron and the nucleus. So here nucleus will not easily gain electron and electron negativity will be low. And the third factor is nuclear charge. Obviously, when the nuclear charge increases, what is the meaning of nuclear charge? Nuclear charge is the positive charge which is present in nucleus. So more positive charge, more number of proton, see, in nucleus, more attraction will be there on outer electron, and as a result electron negativity will be high. So nuclear charge is directly proportional to electron negativity. Atomic size is inversely proportional to electron negativity. Like I told you a couple of minutes back, inert gas. See, what is the basic funda with the inert gas? They have outer electronic configuration completely filled ns2 np6, completely filled outer electronic configuration with the 8 electrons in outer shell. So they are not interested to gain electron anymore, and that is the reason why they do not have any kind of tendency to attract shared pair of electron, and as a result their electron negativity is considered 0. So if someday I ask you what is the electron negativity for inert gases, your answer should be 0. Here are some values for the different species. For the sake of your revision, atomic radius in a group increases, in the period decreases. Electropositivity, that means electron ionization enthalpy, it increases in the group and decreases in the period. Metallic nature increases in the group and decreases in the period. Metallic nature is the tendency to donate electron, and basic nature of oxide also increases in the group and decreases in the period. So these are some properties regarding periodic properties we discussed about this in this unit. In the next class we shall discuss about the few questions which comes in the examination from this topic from the past years. I hope you like today's lecture. Please keep coming and keep studying. Thank you so much.